Hello, everyone, and welcome to this webinar, which was presented by the Sustainability Working Group. And so today we are very pleased to welcome Eloise Marais, who is a professor at the University College of London, and who is a professor of atmospheric chemistry and air quality. So she is leading a group which uses data from multiple platforms to study the influence of human activity on atmospheric chemistry, air quality, and climate. And so today she's going to talk about one of the key aspects of her research, which is the atmospheric impacts of spacecraft launches and reentries. And so I'm leaving you the floor.
Excellent. Thank you, Pauline, for the very kind introduction. I'll take you through, I think, just a very broad overview of this research topic and then dig a little bit deeper into some of the research that my group has been carrying out to try and better understand this aspect. And I've seen that you've had presentations before mine as part of this webinar series that have talked about things like tracking the whole life cycle analysis of the space industry and considering sustainability issues that perhaps we haven't been considering in the past. This focus is really on the impact that pollution from launches and reentries can potentially have on the atmosphere. It's a relatively new, re-emerging field. It was studied in the 90s when NASA was thinking about the potential impact of their solid rocket motors that were sending the space shuttle and other payloads into space. And unfortunately, their Artemis rocket that was launched recently is even bigger version of the solid rocket motors that's adding pollution to the atmosphere. So perhaps NASA has neglected to learn some of the lessons from studies that were carried out in the 80s and 90s. So we've seen, I think, in this webinar series, versions of this time series already showing how certain activities within the space sector are really changing dramatically, especially over the last 5 years. This is a time series of annual launches that are divided into the main countries that are launching rockets. This is from the start of the space era, 1957 to 2025. And I forgot to check exactly what the value is as of today, but as of a few days ago, I think the 19th of April, we've had 93 launches in 2026. So not yet one a day, but certainly increasing over time. And most of this increase is really to launch satellite megaconstellations into space, in particular by what's listed as the US. It's really launches occurring in the US. It's no longer led by NASA. It's really SpaceX and their Falcon 9 rockets that are launching more and more each year. Russia used to be prominent, but now launches far fewer rockets per year. And the Southern Hemisphere has only really started to show up very, very recently. New Zealand is launching quite small rockets, but more and more each year. I mentioned that the main rocket contributing to this growth is this Falcon 9 rocket. So this is a rocket that has 2 stages to it, and it was a technological breakthrough because the first stage was able to demonstrate being reusable, and this has reduced costs of launches and also increased the frequency with which launches can occur at each spaceport. Again, a similar time series showing recent growth, and here focusing rather than on launches, focusing on payloads that are being launched to space largely in low Earth orbit. So this is the orbit that's really becoming increasingly clustered, and we've seen versions of that in this webinar series showing time series of the number of objects just increasing rapidly over time within low Earth orbit. We're causing major clutter from putting these payloads into space, but not cleaning up after ourselves. What this shows is, again, since the start of the space era, and then the bars separate out into different kinds of activities. Some of them are quite similar in color, but the main factor, again, is communication satellites. So this is SpaceX launching Starlink mega constellations into space. And of course, I'm mentioning that we're cluttering these orbits. The only viable way that we have to cleanup space is to send things back to Earth and burn them up through the mesosphere. And during this burning process, we're also adding pollutants to the atmosphere. And unfortunately, what is produced in these higher layers of the atmosphere doesn't stay there. These all eventually circulate or settle back down to Earth. So we're adding more and more metals into the atmosphere, more and more pollutants into the atmosphere. I'll just give you a broad overview of some of the pollutants. If you don't like chemistry, I apologize. I've tried not to inundate you with too many chemical formulae, but here I just want to give a sense of what are the main pollutants and what are their associated impacts on the atmosphere. When we launch things into space, we rely typically on four kinds of propellants: solid propellants, hypergolic propellants, which are rare and only in a few countries. They're not allowed in certain countries because of the toxicity of this propellant, kerosene, and increasingly methane, and then also cryogenic or liquid hydrogen fuel. And below each of these rockets, I've indicated the main kinds of pollutants that are coming from them. All of them are producing something called NOx, or nitrogen oxides. This is because the hot temperature of the rocket plume is converting abundant and unreactive nitrogen in the atmosphere into this reactive nitrogen, or NOx. All of these fuels contain hydrogen. Hydrogen is reacting with oxygen that's also used as the fuel. And so all of them are producing water vapor. Unfortunately, water vapor sounds like it's innocuous, sounds like it's not going to have an impact on the atmosphere, but we're putting water vapor into higher layers of the atmosphere where it is rare, so it's contaminating dry layers of the atmosphere. Then we become more specific with the types of pollutants produced by certain rockets. So I mentioned solid rocket motors. This is Artemis, the recent launch of the astronauts who orbited the moon. And solid rockets also produce chlorine compounds, which are known to deplete ozone in the layer of the atmosphere where ozone is protecting us from harmful UV radiation. And then also a compound called alumina, or Al2O3. This is a particle, and it's a particle that essentially helps speed up ozone depletion. It's essentially reducing the energy barrier that exists for these reactions. And then for solid, hypergolic, and kerosene or methane, these are carbon-based fuels. So they're going to burn and produce something called black carbon, or informally soot particles. Soot particles are dark, they're black particles, and so they're very good at absorbing the sun's incoming radiation. And in that process, it warms up the atmosphere. By warming up the atmosphere, you speed up reactions and you also alter the circulation patterns of the atmosphere. So lots of potential impacts associated with these pollutants. I think I've loosely mentioned these, but just to bring everything together, water vapor is a greenhouse gas. Black carbon is a short-lived climate forcer, so these have concerns for climate. And then nitrogen oxides, chlorine, and alumina can deplete ozone by directly reacting ozone away in the ozone layer. I've mentioned re-entries as well. So this is re-entry ablation, or just very hot re-entry that takes place that also produces a whole range of pollutants. This is coming from discarding rocket bodies that are not reusable. And then this comes from payloads that also have reached end of life. And they, after 5 years of reaching end of life, need to be re-entered through the atmosphere to discard of them. Ideally, this is so that these compounds, these objects demise completely and it reduces risk to life on Earth. But if we have complete demise, all we're doing is essentially depositing a whole range of pollutants into the atmosphere. This is also NOx, or nitrogen oxides, coming from ablation. Again, it's because of the high temperature process. There's a shock wave that's generated when these objects re-enter, and this energy is also able to convert unreactive nitrogen in the atmosphere into NOx. And then because most payloads and rocket bodies are made up of metals and metal alloys, they're going to produce a whole range of metal oxides depending on those metals: copper, aluminium, titanium, and so on. And then also there are resins and other parts to these payloads that produce black carbon or soot particles, and even more seemingly exotic compounds like ammonia. Ammonia is a pollutant that we know from the surface of the Earth comes from agriculture, but it's also potentially can be formed from ablative re-entry. We tried to understand the mix of pollutants that could come from ablation by doing things like modeling. It's really hard to observe the atmosphere at about 50 to 80 kilometers and above. And so these models can tell us by altitude what mix of pollutants could be produced. For me, this plot is flipped. It's from another paper. I prefer altitude to be on the y-axis, but that's okay if we can just imagine that this is going from the sort of stratosphere to the lower layers of the mesosphere. The original object that's modeled here includes titanium, aluminium, vanadium, iron, and so on. And so there's all these titanium oxides and so on that are produced from the ablation process. We don't really have a full understanding of the emissions that are coming from ablation because we don't have this level of detail of what original objects are made of. We probably know rocket bodies a little bit better than satellites, but satellites include sort of industrial secrets, proprietary information that we don't have access to as researchers to be able to put this kind of information into our research. There have been studies, though, that have started to look at the pollution that's coming from ablation. So there are high altitude aircraft which have on board instruments, and these instruments can make a whole lot of detailed measurements. One of these instruments is a mass spectrometer style instrument that can actually measure the composition of individual particles or aerosols in the atmosphere. This aircraft goes as high as the lower stratosphere, so about 16 kilometers altitude. And when they sampled aerosols in the stratosphere, they identified key contaminants that are associated solely with space sector payloads or satellites. So hopefully I've written it down here because I'm not going to remember. These are such exotic chemicals. Niobium and hafnium are amongst the chemicals that don't come from natural sources. They are natural inundation that's typical of the upper layers of the atmosphere is from meteors. Aluminium comes from meteors, but these types of chemicals do not. And when they collected a whole lot of samples, they identified that about 10% of all stratospheric aerosol particles are contaminated with metals that are coming from spacecraft re-entry. And this is a really important number. So this is for 2023. 10% is 1 in 10. And we're not yet at the stage where we're making full use of low Earth orbit, where we're not doing a lot more to clean it up by burning more through the atmosphere. We anticipate that that 10% value is going to increase steadily as we continue to launch a whole range of payloads into low Earth orbit. There are other studies that have started to happen since that paper was published that have also used other instruments to show that we can actually detect enhancements of pollutants in the atmosphere associated with re-entry. This was a study published earlier this year. And what they did was used a LiDAR remote sensing instrument based somewhere in Germany, and I apologize, I haven't written down the slide, so I cannot recall. It's not intended to detect space sector pollution, but by coincidence, it did pick up a signal of titanium that was way above what they would have expected from any other potential sources of titanium. They were able to confirm that this is a true signal, and they were able to use back trajectory modeling to say that the signal is more than likely associated with the re-entry ablation of an upper stage Falcon 9 rocket. Lithium is not the most dangerous pollutant coming from re-entry ablation, but it was an important demonstration of the ability to use these kinds of surface-bound instruments to make these measurements. So we could potentially expand our network and develop a network dedicated to space sector pollution on the ground. All we need is funding. And just to bring everything together, I mentioned that the main issue with the space sector is that these are metals that are not very common. There's processes that happen that are quite distinct compared to earthbound pollution sources like ships and cars and coal-fired power plants. Rockets and re-entry ablation are injecting pollutants into just about every single layer of the atmosphere. And in those higher layers of the atmosphere, those pollutants can stay there for 3 years, even more, depending on the type of pollutant, compared to a few weeks for that same kind of pollutant closer to the surface of the Earth. And the longer a pollutant stays in the atmosphere, the bigger its impact. And so we have these almost 200-fold greater impacts from these pollutants, from these re-entry and launch processes, because they are able to hang around in the atmosphere for longer. The major loss processes from the atmosphere is really just this large scale circulation patterns that eventually bring air from higher up, lower down, and then also very slow gravitational settling. And as these pollutants settle, they're passing through this protective ozone layer, and in the process, they're able to deplete ozone. We've been very successful as a global community in regulating pollution that could harm the ozone layer as part of the Montreal Protocol, but unfortunately, the pollutants that come from rocket launches and from re-entries are not controlled through that regulation. And so we don't have any mitigation measures in place that could effectively reduce the amount of pollutants that are being added to this layer from the space sector. I think I've mentioned this a few times already, but just to reiterate that it's really the combined impacts of re-entry and also launch that we're concerned about, because something like black carbon that mostly comes from launches can change atmospheric circulation patterns and warm the higher layers of the atmosphere, which can then exacerbate the impacts of pollutants coming from re-entry ablation. What we did at UCL is use a model that we've contributed to using and developing to try and quantify the impact of mega constellation missions on the atmosphere, focusing on ozone depletion and on climate. We've already built what's called an inventory of the air pollutant emissions that come from these processes, and we published this in a Nature subsidiary journal in 2024. I include links to this later in the talk. We also were able to use this inventory to categorize emissions that would be associated with mega constellation missions. So not just from Starlink that I've mentioned already, but also other mega constellation launches by companies and space agencies in China, as well as in the UK. We wanted to look at the long-term impacts of sustained growth in the mega constellation emissions. So we projected emissions as well to 2029 to get a full decade of emissions. And we were also able to assess these emissions against high altitude aircraft observations. So making opportunistic use of aircraft campaigns that took place. They actually were able to measure a plume coming from a Falcon 9 rocket launch by intercepting it at about 16 kilometers. We put these emissions into what's called a chemical transport model. This model is also coupled to a radiative transfer model to calculate the climate impact. And then what we did is we quantified the atmospheric impact. So what we were interested in is looking at the percent depletion of ozone in the layer that's protecting us from harmful UV radiation, but then also the radiative forcing, the climate effect associated with adding these compounds to the atmosphere. I won't go through this in too much detail. I think just for due diligence and completeness, I'm showing the emission inventory method that we put together, the sort of processing pipeline that we published in 2024, where we made use of existing databases that are tracking launches and re-entries. We used all sorts of reports, press releases, Twitter feeds, mission guides, launch live streams, and so on. We were as creative as possible to gather as much data as we could to fill data gaps and to also cross-check data sets to build the best emission inventory we possibly could. We mapped the location of launches and re-entries, and we also mapped in vertical distribution where the propellant emissions and re-entries are taking place in terms of altitudes in the atmosphere. I think I've already mentioned this, but perhaps just to call out someone called Jonathan McDowell, who has for years and years sustained a catalog of launches and re-entries that we're incredibly reliant on to put together this emission inventory. And we collaborated with him when we published this paper. Just to give you a flavor of what this kind of emission inventory looks like, we have information about the vertical distribution of launch emissions. We do this by mapping the vertical distribution of propellants. Ignore this above GeoSchem and GeoSchem text for now, but what it is showing is just the percent of propellant that's consumed within each altitude. And this provides us with the information we need to put together an inventory that represents emissions from these sources in 3 dimensions. We compared these sorts of profiles to profiles that we would estimate from launch live streams. So we first started off with a very manual approach of watching these live streams from things like Falcon 9 launches and mapping the amount of propellant consumed with every 5 kilometers of ascent. And then we discovered that someone had actually prepared a Python script to scrape this kind of information from these live streams. So we went from doing this manually to doing this in an automated approach so that we could scale up to 32 live streams for a single year. We found that the emission profile that we use, which is in green, is quite consistent with the values that we estimate from these launch live streams. We also wanted to distribute where re-entries are taking place. And so there was a lot of random distribution and guesswork that we had to do because many of these re-entering objects, we don't have clear and detailed information of the exact latitude and longitude where they're re-entering. So this spotty graphic that I'm showing here, this map is indicating where we know an exact location, where we kind of know an exact location based on the political or physical area that's been reported, where Falcon reusables are entering. These are all very close to the spaceports where they're launched. And then a random allocation that we had to use based on information that's provided in the re-entry database. And so our map shown here, because it's got a random component, could be different with each iteration. But what we do show is that when we put this together, the re-entry mass and number of objects is quite concentrated around the equator, which we would expect from how objects re-enter the Earth, so due to the obliquity of the Earth. I'll ignore the second map that's showing here. That's just distributing onto a fixed latitude and longitude grid, the re-entry mass. These maps as well are just showing this information of where re-entries are occurring, how much mass is re-entering, and just an indication of how this is increasing year on year. So in 2020, there were 878 known re-entering objects. In 2021, this is increasing to almost 1,100. And by 2022, it's 1,650. Year on year, this is increased, adding more re-entry mass. What we find if we also look specifically at the mega constellation objects that are re-entering, this has gone from about 20% of all re-entering object mass by 2020, the sort of first year that this mega constellation era establishes itself, to about a quarter by 2022. And again, that's just increasing over time. When we compare this to the natural influx, so meteors, the natural mass that's being input into these higher layers of the atmosphere, by 2022, we're estimating that the space industry is representing about 40% of this natural influx. So we're moving the upper layers of the atmosphere from natural or remote or pristine to increasingly anthropogenically influenced. Our last Earth system region that was pristine and relatively unaffected by pollution is now changing rapidly. I might skip this slide. It's a little bit similar to the previous one showing the vertical distribution of things. Perhaps I'll just emphasize a little bit here. But this is the vertical distribution of the different pollutants that are coming from re-entry and launches. And so perhaps I'll highlight black carbon or soot particles because I bring this up later. These are these very, very efficient climate forces. And what we see with black carbon is that the majority is actually being emitted into the higher layers of the atmosphere. This is because the rocket just becomes, as a whole, just becomes increasingly inefficient at converting carbon to CO2. So that would be the full combustion process as it ascends. And so more of that carbon is making black carbon that's being released to the atmosphere. The higher we're putting this black carbon into the atmosphere, the more effective it is at warming the surrounding atmosphere. And so this has implications for climate. I meant to go to this next slide. So what we're doing with this emission inventory that we've painstakingly put together and also has undergone rigorous peer review is that now we've spun it out to an online emissions tracker. So what we're doing now is tracking these emissions all the way from 1957, the start of the space race, to the most recent year available. So here we have 2024. 2025 we could have updated with, but what this is showing is a time series of just how the pollutants increase with the first space race. They decline over time until we get to an era where we have reusable rockets and it becomes cheaper to launch things, and the mega constellation era kicks in, and we start to see this exponential growth in pollutants. As well as CO2. So CO2 is the gray portion that's increasing the most. I've just included a QR code. If you wanted to take a look at it and play around with it, you can change the number of compounds that you look at to focus on a particular compound if you wanted to. And you can look at this time series in finer time resolution, monthly instead of annual. Similarly, we've put an online emissions tracker together for re-entries, and this has just been completed. So you're the first to see it presented. And this again is showing how this re-entry mass has increased over time. I should point out that this is not just pollutants, but also an attempt at counting unablated mass, the mass that's coming back to Earth that poses a risk to us. And this risk is increasing over time because of the sheer number of objects that are returning. Again, this is annual. It's also since 1957. And on the online emissions tracker, you can remove and add and change pollutants if you want to focus on particular things, and also look at this at a monthly resolution. Of course, it's missing a lot of the metals that come from ablation. There isn't just aluminium oxides. It's also copper oxides, titanium oxides, and so on. So it's relatively incomplete. And again, these are just the QR codes if you want to play around with the emissions inventory, and just a link to the actual URL that these QR codes send you to. Perhaps this is worth presenting. I know this gets into the sort of meat and bones of the particular research that I do, but what is important is that we finally had this rare opportunity to evaluate our emissions against these aircraft observations that intercepted plumes. So they were permitted to fly an aircraft a few minutes, about 30 minutes after Falcon 9 launch, and try and find the plume and make measurements to see how much the plume is how much concentrations of pollutants in the atmosphere are enhanced as a result of these plumes. They flew at about 16 kilometers altitude. So this is in the lower stratosphere. And what we were able to see from these measurements is enhancements in water vapor and enhancements in the two components that make up NOx, or nitrogen oxides. These are just highlighting the time series of the flight measurements that were made very close to intercepting the plume, showing the first intercept and then the second slightly smaller intercept. What we did was essentially fit plumes, Gaussian plumes, to these measurements to try and estimate the emissions associated with this particular rocket launch. We scaled it by water because water is conserved throughout the altitude in which the launch occurs. And we estimated values that are about 6 times more than we actually have in the inventory. So it indicates that we're actually being way too conservative with our estimate of emissions of pollutants from this inventory. And the reason this is that we're very reliant on exceptionally outdated data to put together these inventories. These are reports that we use that were published in the 1990s and early 2000s, and they're largely based on a different kind of rocket that burns a different kind of fuel. And so there's this critical need to be able to gather far more of these measurements so that we can build far more reliant inventories of emissions. But of course, funding is an issue, and this was done by NOAA in the US. And so they are experiencing severe cuts in their funding. I might skip this one. I think I've covered a large portion of this. We use a model that represents atmospheric chemistry and then also physical processes in the atmosphere. And what we can do with this model is essentially anyone can use and develop this model. You can download the source code from GitHub, and you can edit the source code to apply the latest science within your area that you're researching. The model is called GeoScam. It's a publicly available model. It's used by hundreds of people around the world. But it's used mostly for processes that happen closer to the surface of the Earth. No one has really used it at all since us for rocket launches and re-entries. And so what we do is we update it to include new compounds, alumina that isn't normally in the model because it's not needed. And we also update it with new processes that have been observed with these rare aircraft campaigns. And one of these processes is that aerosol particles that are produced from rocket launches and reentries are actually very, very quickly taken up to existing aerosols in the stratosphere, so around 10 to 50 kilometers. And this is really important because it means that it increases the size of these stratospheric aerosol particles, which means they can potentially deposit out of the atmosphere faster. So it changes their lifetime. The size increase also makes them more efficient at depleting ozone. And we have very dark particles being ingested into the center of these sulfate particles. And we know from climate science that this causes something called a lensing effect that actually enhances the climate forcing associated with these black carbon dark particles. All of this information we represent within the model so that we can do a better job at representing the atmospheric impacts associated with rocket launches and re-entries. This is quite a busy slide, but what I wanted to just show was some way of illustrating this geoscam model that we use. It's a chemical transport model. It already has the capability to couple to a radiative transfer model, which calculates the radiative effect for estimating climate. And we can run it into the future, essentially just using meteorology for a single year. Not projecting future meteorology. We use something called offline meteorology. It comes from NASA. It's a NASA meteorological product. And then also the model includes an exhaustive suite of emissions that are very, very familiar to us. But of course, it doesn't include rocket launches and re-entries. And this is something that we add to the model. There's also a lot of power that you have in running these kinds of models. So what we can do is we can run the model with absolutely no rocket launches and re-entries. We can run it with all rocket launches and re-entries, and we can run it with just the mega constellation associated rocket launches and re-entries. And by doing this, it enables us to essentially calculate the ozone depletion and the climate warming or cooling that would be associated with mega constellations only. Um, Again, this is quite a bit being shown. I might skip this and just say that when we look at the effect on stratospheric ozone, so this protective layer, we actually find that there's only a 0.03% decline in stratospheric ozone, really, really small in comparison to the regulated ozone depleting substances that are regulated through the Montreal Protocol of about 2%. And this is in large part because we're using mega constellation missions are using rockets that are burning kerosene that doesn't produce a lot of ozone depleting compounds. That's the case for now, but that's going to change over time as more and more people, more and more companies are considering launching mega constellations into space, and many of them are considering launching these with solid rocket motors that are producing a lot of chlorine that depletes ozone. So for now, the ozone effect is quite small, but we suspect that this is going to change as more and more companies launch. mega constellations. What is more intriguing is the radiative forcing or the climate effect that occurs. I don't know how familiar everyone is with these quantities that I'm showing here associated with radiative forcing, but essentially this is the typical unit that's used, watts per meter squared or milliwatts per meter squared. And if it's positive, it's indicative of warming. If it's negative, it's indicative of cooling. There's two quantities that we estimate. One is called instantaneous radiative forcing. So this is the immediate change that would occur as a result of adding things like black carbon to the atmosphere. But then once this is added, this warming occurs and the atmosphere re-equilibrates. And after it re-equilibrates, there's an adjustment to the stratosphere, and there's an associated longer-term radiative forcing due to the stratospheric adjustment. In essence, the sign changes. So the initial effect is warming, but then over time it flips to cooling or negative radiative forcing. And so we can focus on this column on the right because this is really more representative of reality. And what it is showing is, in essence, we see a cooling effect. We see a cooling effect from all missions of about 6.4 milliwatts per meter squared, and the satellite mega constellations account for just under 50% of this cooling. Cooling sounds like it's a good thing. We're trying to reverse the warming that's occurring as a result of producing large quantities of greenhouse gases closer to the Earth. But unfortunately, there are many unintended consequences of this kind of cooling occurring in the way that it's being done with rocket launches and re-entries. We change atmospheric circulation. We potentially deplete the ozone layer. What this is really is a type of geoengineering. So the geoengineering plans that involve aerosol injection is essentially injecting aerosols above the tropopause, so into the stratosphere, causing cooling closer to the surface of the Earth. But we know that we haven't adopted these on a large scale because of the many unintended consequences for the atmosphere. So this is almost like an unvetted geoengineering experiment occurring. We can also look at what contribution the different kinds of pollutants are making to this warming. And essentially, if I just give you the main result from this slide, it's really black carbon or soot particles because they're so good at warming the atmosphere. So this again is the initial radiative forcing or instantaneous radiative forcing that causes warming. The stratosphere adjusts, the atmosphere re-equilibrates, and the sign reverses. But again, black carbon is the main factor causing that reversal in sign. There are other things that happen as well. We deplete ozone, and so ozone is also a greenhouse gas, and so it contributes to changes in radiative forcing. We're also growing stratospheric aerosols. Aerosols are also climate forces, and so that makes a contribution, but they're much, much smaller than the effect of black carbon. I think I've mentioned this already, that the satellite mega constellation missions, even though they've only been around in our simulation for 10 years, compared to a space race that started in 1956, they already account for almost half of the radiative forcing after adjusting for changes in the atmosphere. So really, really large inroads to affecting the atmosphere. I'm tempted to skip the slide because I've said this in words in the previous slide, just indicating that these are like uncontrolled or unregulated geoengineering experiments. So if I just summarize the key findings from our research that are relevant to understanding the atmospheric impacts of rocket launches and re-entries, we find that in general, global ozone depletion is quite small, especially in comparison to the about 2% depletion that comes from regulated ozone depleting substances. We find that this black carbon that becomes coated with sulfate once it's in the stratosphere is very effective at absorbing the sun's incoming shortwave radiation and instantaneously warming the atmosphere, and then eventually causing a negative forcing, which is potentially cooling the troposphere. And then I mentioned this already, SMC or satellite mega constellation missions have only existed since about 2020, but already they're accounting for about half of the climate effect. And of course, there are other ambitious plans to put even more mega constellations into low Earth orbit. So that half is going to eventually increase substantially to almost dominating the climate effect. Of course, I have to admit that this is a modeling study and we have really few, very, very few observations to constrain and validate the model. So large uncertainties do exist in our ability to represent all of these complex processes. And so there is this really strong appeal, not just to funding agencies, but also to researchers to study these effects in the lab, to make measurements in the field, to also develop finer scale or smaller scale models that could help model the sort of plume chemistry that's taking place during ablation and re-entry. I've included links to the paper that was published in 2024, to also the data. We put all of our data online so that other people can access it, scrutinize it, hopefully collaborate with us if they use it. And then also our atmospheric impacts paper is just about to appear as a peer-reviewed paper. So here I'm just sharing the preprint, but it has recently been accepted. And perhaps I'll close with some of the key challenges that we're experiencing in this field. Um, One is that currently the magnitude of pollutant emissions that are coming from rocket launches and re-entries is far, far less than earthbound sources like ships, traffic, and so on. Um, and the issue is that, of course, the impacts are much larger per unit mass of pollutant emitted because these pollutants can stay in the upper layers of the atmosphere for so much longer than earthbound sources. And so the space industry doesn't need to grow to the same size as some of these earthbound sources to have a similar impact. Um, there may, of course, be other impacts in the higher layers of the atmosphere related to space weather and so on, but it's really an area where I'm not an expert, but there are experts who are interested in exploring this aspect further. And then, of course, the challenges of suitably observing layers of the atmosphere that are way above us. We are very reliant on remote sensing. And then currently, because we don't have dedicated networks to look at this problem, we rely on these chance encounters and also rely heavily on theoretical under constrained models. And there's a lot of concern over the activities that are on the horizon, which are very difficult to predict because they seem so outlandish, like putting AI data centers into space, advertising on the moon, having these sort of point-to-point transport patterns. I'm using the wrong term, but I can't think of the correct word now. And so it's very challenging to explore what the implications might be for this unregulated pollution, or whether we could potentially reach any tipping points with these kinds of activities. Then, of course, there are proposed so-called cleaner options, like bio-derived propellants, and then also wooden satellites that are being advertised. But the issue is that these are unfortunately not pollution neutral. Bio-derived fuels like kerosene and methane produce black carbon, and water vapor. Wooden satellites are going to burn up through the atmosphere and in the process produce a whole range of pollutants, including black carbon. Because it's like burning fuel wood. When you burn fuel wood on the fire, you're also producing a whole range of toxic pollutants. Then also industry is adopting fuels that lack emissions measurements, in particular liquid methane. We can theoretically estimate what kind of emissions are coming from burning liquid methane, but it would be great to validate this theory against measurements. And overall, science just can't keep up with the industrial advancements that are occurring. We don't have sufficient funding. We have the right kind of people and the right kind of expertise. And we meet often to discuss this topic and grow our laundry list of issues and uncertainties and aspects that we need to study. But we really do need far more dedicated funding to explore this topic. And provide far more measurements that are critically needed. And so the issue is that if the science can't keep up with the industrial advancements, we also can't then provide the evidence that's needed to inform legislation so that we can mitigate further harm to the atmosphere. Um, that's the end of my presentation. And of course, if there are any questions, I'm happy to take them. I know this is a very small audience, so if there aren't any questions, that's also okay. And perhaps I will just jump to my introductory slide where I have my email, and anyone who has any additional questions is more than welcome to email me to ask. Thank you very much for your time and attention.
Thank you very much for this very interesting talk. So yes, if you've got any question, could you please type them in the chat, or alternatively, you can just ask us to unmute you and you could just talk directly. And I just had a question to begin. One of your last point was that science doesn't really have the evidence necessary to inform legislation. And what do you think would be the one thing that you would need, or the most important set of data that you would need to?
Oh, there's too many pieces of important data that are needed. I think something that we don't have a good handle on is the sort of initial production of metal oxides from re-entry. Or just metals, because I don't think they're just going to be metal oxides, and how that evolves as the re-entry process occurs, but also as these metals mix within the atmosphere. We have very little information about the composition, distribution of these different pollutants. And then also, in addition to this, if they do form particles, in what process are they forming particles and how big do they grow? And what is the sort of relative distribution of those populations of different sizes of particles? That would focus in particular on re-entry.
Okay, thank you very much. I did have a second question. At some point, you showed that one of the effects that was expected is a warming of the atmosphere, but then that it would re-equilibrate to cool. And I was just wondering if you could say a few words of how exactly does the atmosphere re-equilibrate?
Yeah, this unfortunately is not my area of expertise. This is really the area of expertise of one of my co-authors, Seb Eastham, who really worked at putting this aspect, known aspect, into the model that we used. But essentially, what's happening is that on quite short timescales, the stratosphere is responding to this initial warming. So if we think about other parts of the Earth system, something like the ocean has sort of response times that are much, much longer. So we don't necessarily need to think about something like the ocean re-equilibrating, but the stratosphere re-equilibrates. And in that process, the sign of the warming changes to cooling. So this is really the science behind geoengineering.
Okay, thank you very much.
Sure.
Does anybody else have questions? Oh, sorry. Okay. So, Ingrid has a question. Do you have any thoughts on how we can convince funders to provide more resources so that we can do the work needed to inform policy decisions?
Yeah, I mean it's an unfortunate era because often the science funding is there's often a lot of science funding available to pursue these kinds of topics in the US. Uh, but that's not the case currently. I think that we have to just find ways in which we can meet with and discuss this kind of topic with research program directors to to communicate exactly why this topic is important, why it is timely, and what funding would do to facilitate addressing severe knowledge gaps. Within the UK, I have at least been successful in having discussions with a relatively new funding source called ARIA, where I met with the program director and essentially pitched this topic as an area of concern and where my kind of research expertise could be used. And I now have funding to do what's called a seed project. So for 1 year, I do something that's high risk but high reward and could potentially lead to a research project. Within Europe, there's Horizon Europe, and I think it's finding opportunities to convince the funders to have focused topics on this particular research field. So it's not really a straightforward answer because unfortunately different funding agencies operate in different ways. But certainly if you're publishing in this topic, if you're communicating this topic at these kinds of networks and venues, and also at very large conferences, I think the message is going to get out there that a necessary aspect to this is receiving sufficient funding.
Thank you very much.
Sure.
And then Sophia has a question, which is, have you already reached legislators? And if so, could you explain in more details what would be the ideal process of adopting legislations?
I missed the first bit. I think you were clearing your throat and just didn't hear the
Oh,
words. No, that's
sorry.
fine.
Have you already reached legislators?
Okay. Yeah, one of the issues, of course, is that currently, so the way legislation works is right, we see a problem, it becomes a big enough problem that it's already had a severe impact, and then we implement legislation when it's already too late, and we have to do a lot of cleanup. So this has happened for, I can't see an air quality policy example where that hasn't been the case. And so we're at the stage where the atmospheric impact is not yet that bad for legislators to, I think, pay sufficient attention. So it's a case of not just making legislators aware, but also changing the approach to which we legislate. We should be mitigating before this becomes a problem. Um, Scientists who are working on this in this field are trying hard to get that message out there, but because there isn't clear legislation focused on this topic currently, it is a little bit challenging. We've got the attention of the UN. They are very interested in getting the message out that this is a concern and thinking about ways to legislate, but legislation moves slower than industry as well. So I'm not sure that we will have legislation in place before it becomes a really, really large problem.
Thank you very much. So we're nearing the end of the hour. So if anybody has any last question, could you please just type them or ask them directly? And if not, thank you very much once again to Eloise for this very interesting talk.
Oh, thank you.